A very good evening to all members gathered here. Today we are in session number 6, Design of Coupling Joints from the course Design of Machine Elements. Let us see some of the basic important features of coupling joints in machine design. So now we will have the overview design of coupling joints. What do you mean by the coupling joint? So it is a mechanical machine element or a device which connects two shafts by allowing them to transmit torque and motion through rotation. So designing a coupling involves various selection of appropriate type of material and estimation of design dimensions to ensure it whether it meets the proper load requirements and operating conditions. So the following key consideration includes the type of misalignment the coupling needs to accommodate and the torque it must transmit and the operating speed at which it produces the motion. These are some of the key factors which influence the successful design of a coupling joint. What are the classification of coupling? So basically there are two types. One is rigid coupling, the other one is flexible coupling. Under the category of rigid coupling, so we can say flange coupling, sleeve coupling like that. So flexible couplings, we can consider universal joint, old arms coupling. These are some of the classical examples given under each category. So what is the difference between rigid and flexible coupling? Rigid couplings produce a torque directly between the shaft without any ability to accommodate the misalignment. So it is called as protective type coupling. Flexible coupling can able to tolerate some misalignment and are designed to absorb the shock loads, and also it will try to have a better dampening when the shaft is considered to be rotating by transferring the power and torque during dynamic conditions. The misalignment can be a parallel, angular, or axial. So these are the different types of adjustments we can able to do it when the power is being transmitted between the two shafts. Whereas in rigid coupling, this kind of provision is not kept there. Now let us see some of the design considerations in the coupling joint. First one, we have to determine the shaft diameter based on the initial torque transmitted and the material properties. Next one, we have to calculate the flange dimensions. Then keyway dimensions. Calculate the keyway dimensions depending on the shaft diameter, torque, and the material properties in order to have a safe and secure connection. Then bolt dimension. Design the bolt connections including the diameter of the bolt and spacing based on the torque and the factor of safety. Then next one is material selection. Choose the appropriate material that can able to withstand the operating conditions like temperature, vibration, and load. And safety factors. Apply appropriate safety factors in order to overcome uncertainties in loading, material properties, and manufacturing tolerances. And operating conditions. Consider proper required speed, torque, misalignment, and a better operating environment when selecting the coupling type and dimensions. The next design is alignment. Ensure proper alignment of the shaft to avoid more excessive stress on the coupling. Not have a comfort fit. Space constraint. Consider available space and ensure whether the coupling will fit within the designated area or not. So these are the different design considerations in coupling joint. So what are the basic design calculations normally a coupling joint will have? So we have to check for tensile failure, shear failure, and crushing failure. So we will see with the example problem now. Consider a rigid type coupling which is used to connect two machine shafts. The input shaft transmits 37.5 kilowatt power at a speed of 180 RPM to the output shaft through the coupling. The service factor for the application is 1.5. Select suitable material for various parts of the coupling and estimate various design parameters of the design. So here they have given the power and the speed of the shaft and the service factor according to the torque transmitted by the shaft. Now we have to find out the remaining dimensions of the coupling design. Let us see. So the given data, the power transmitted by the shaft, then next one is maximum speed of rotation, then service factor. The material is considered to be cast iron, the flange material. So the allowable shear stress, that is the design stress for cast iron, the shear stress 50 Newton per mm square. Shaft, keyway and bolt material is made of mild steel. Allowable shear stress for mild steel is 40 Newton per mm square. Allowable normal stress of mild steel 80 Newton per mm square. So these are the various design factors we are going to consider during the calculation part. First step, find out the torque from the power equation. So using the power equation, here we can able to witness the power equation formula above. Using this formula, find out the maximum, the calculated torque. So this is the value, the quantity of maximum that is calculated torque. So you need to find out the design torque of the coupling. So the service factor is given 1.5. Multiply the service factor with calculated torque. So you can able to find out the allowable torque of the coupling design. Next step is find out the shaft diameter from the torque. So use this formula and calculate the shaft diameter. So it is found to be 73 mm, the diameter of the shaft. Then calculate the coupling dimensions as per the standard proportion. What are the various dimensions of coupling? Outer diameter of the hub, pitch circle diameter of the bolt, outer diameter of the flange, thickness of the flange, length of the hub. So they have given the formula equation accordingly. So substitute the values in the corresponding equations and find out the eligible dimensions of all the parameters. The next one is calculate the keyway design. Find out the size of the keyway, optimal size of the keyway design. The size of the keyway is selected based on the shaft diameter from the data book. Already we have calculated the shaft diameter 73 mm. So refer this value in the PSG design data book, page number 5.16, and check for shear stress and crushing stress in order to validate the size of the keyway, whether it is good fit or not. So these values are taken from the data book from the corresponding page number 5.16. So the width of the keyway 20 mm, thickness, that is height of the keyway 12 mm, length is 110 mm. Here the keyway length is considered equal to hub length. That is the assumption taken in this design. Now find out the design calculations. So check for shear stress in the key. Since the allowable shear stress is 40 and the calculated shear stress is 37.2, which is very safe, less compared to the allowable shear stress. Next, find out the crushing stress across the keyway design. Here it is comparatively more. The calculated value is more than the allowable value, so it is not safe. So you have to select the higher thickness value for a keyway. See, assume 20 mm thickness. So for a 20 mm thickness, again you redesign the crushing stress calculation and it is proven to be safe. So the final dimension of the keyway design is 20 by 20, length is 110. This is the optimal design of the keyway. Width is 20, height 20 mm, length 110 mm. Next one is design of bolt. The size and number of bolts are selected from the design data book from the corresponding page number 7.107. From this corresponding page number, so take the bolt diameter, number of bolt, then find out the shear stress acting on the bolt using the proposed formula and check for shear stress. So the design is safe. The allowable shear stress is less than the calculated shear stress is less than the allowable shear stress. Then check for crushing stress for the bolt design. This is also considered to be a positive result. The design is safe. So in the case of bolt design, all the values are more feasible. Check for hub and flange design. So check for shear stress for the hub. Check for shear stress for the flange design. So apply the proposed equation and find out the calculated value of the shear stress in the hub and compare with the allowable shear stress for the hub. So it is safe. So 5.2 Newton per mm square is less than the allowable shear stress for the hub, 50 Newton per mm square. So it is safe condition. Next one, for a flange design, again do the same calculation. Check for shear stress for flange. We apply the equation which is shown here and calculate the value 2.4 Newton per mm square. So it is also considered to be a safer design, which is less than the allowable shear stress for the flange. Hence, the design is safe. So, in this problem, we have proved that the design of the protective type, the flange coupling, that is a rigid coupling, for a given power and speed, so the service factor, and also depending on the material selection, we have tested the different types of the stress acting on the various structure of the coupling joint by referring the corresponding material and the formula from the data book, design data book. And finally, we have proved that the design is safe for all the parts of the flange design. Now, what I conclude in essence as overall, the coupling design means connecting two rotating shafts by providing enough flexibility for misalignment in order to have end-to-end movement freely. The primary goal is to transmit power more efficiently and reliability between the two moving shafts. So with this information, I thank all the members. We will meet in the next topic, design of spring elements. Thank you one and all.